I will feed them to Arno. The recording has started. So yeah, and also if there's any small question that we can quickly answer, I can answer it or somebody else from Bitgrace can answer it right away. But more the bigger questions we can handle afterwards. Yes, so I would like to give the floor to Arno. If you don't know who he is, well, he's one of the founders of Bitgrace. But he loves to tinker around with stuff within the company. And I think we're pretty much set. So whenever you're done or ready, go ahead.
Thank you. Can you hear me?
Yes.
I assume so. Very good. So, welcome to this Autonomy and App Layer workshop. So, my name is Arno. I'm from Bitgrace. And in this workshop, I will try to go through ways to actually control the Crazyflie autonomously. And by autonomously, I mean by a machine, making a program that controls the Crazyflie even at a high level without having the need to a human to control it. Need to be on the right screen. Good. To do so, we will be looking at the push demo. The push demo is a demo we've done when doing the multi-ranger. So it's a demo that's using a Crazyflie, a multi-ranger deck here, and a flow deck. The multi-ranger deck has time-of-flight ranging sensors facing front, back, left, right, and up. And the flow deck has a motion sensing sensor and a time-of-flight sensor that allows the Crazyflie to hover and stabilize itself, at least in a relative position. In this demo, we're implementing a very simple algorithm so that if the Crazyflie detects any object in any of the sensors around it, it will fly away from the obstacle. It allows to push the Crazyflie around. It's a really nice demo because it's fully autonomous behavior, very easy to explain, very easy to show, and very easy to implement. So it's a perfect demo to study autonomy. So how this will that be architecture? The multi-ranger in the Crazyflie measure ranges to all in all directions and gives this measurement available as a log variable. We have a log subsystem in the Crazyflie that allows you to pull variable values at regular interval. We need a push algorithm that implement what we want to do here, pushing the Crazyflie around. And this will result in generating set points for the Crazyflie. So where do we want the Crazyflie to go? And this will be then fed to the control loop in the Crazyflie, and the Crazyflie will actually follow order. Multi-ranger, log, control loop, and set point, those are in the firmware already. They are ready to use, and hopefully they are good enough for use cases. Push algorithm is what we're going to write, and the question is where to write it. Like we can do it on the PC as a Python program, or we could do it in the Crazyflie firmware, and we will go through both here. So we'll start with the PC, which makes the most sense because the PC is not an embedded system. It's much easier to program with, and you can debug, and you can printf, you can do a lot of things very easily. So it's very good to play around with. From Python, we've made a Python package called cflib that handles all the communication with the Crazyflie. I have tried here to show a little bit how the protocol stack would work, how everything would work. You don't have to care too much about the details, but it's very good to know that those details exist. So you're going to write push.py program that's going to use a cflib. Cflib provides you with a Crazyflie object that actually exposes the API of the Crazyflie. And this is using what we call a radio link, which implement the actual radio communication, safe radio communication with the Crazyflie. And over radio in the Crazyflie, we have the radio link, and we have a bunch of subsystems that are that we're able to communicate with. One of those is a logs system, which is where we're going to talk to the multi-ranger. And actually a subsystem is called commander, where we send a set point, and that actually will then push the set points to the control loop. You will need to give a URI when connecting Crazyflie. That's an important detail. We've done that so that we could have this lib independent of the transport. You could use exactly the same function when you connect to the Crazyflie using either USB or radio, or why not UDP or whatever in the future. The radio URI looks as such: radio 2.//0/AT/2 mega/C7777777. And I noted here what things mean. So the first 0 is a dongle. You can have multiple radio dongle to your computer, and it can be useful when connected to multiple Crazyflie to add more radio dongle. As a rule of thumb, we usually set at about 3 Crazyflie per radio. And we may have some communication bugs that makes it even more important to stay with that right now. 3 Crazyflie per radio is good, rough thumb. 80 is a channel. It's 80 megahertz over 2400. It's just a channel. If that doesn't work well, if there's collision with Wi-Fi, you can change it to get better connection. 2 mega is data rate. It's a default data rate, and we should all use this one. The radio support 1 mega and 250K as well, which have longer range in theory, but they also have longer packets, which means that there's more chance of collision with Wi-Fi. And I mean, 2 mega works for all intended purpose. And E7777 is the actual radio address. If you're controlling multiple Crazyflies, the best is to actually change this address so that you do not risk any collision. Even if you have different channels, we have seen crosstalk between channels. So if you're controlling multiple Crazyflie, one address per Crazyflie is the safest. Yes, and then the CFlib implements all the details of the communication after that. Some deck have specific drivers. For a lot of things, log and param, we also have a param subsystem to set parameters in Crazyflie, are the API. For a lot of subsystem or a lot of decks, you will have log you will basically log things. Multi-Ranger has a small helper that allows you to actually read value a little bit more easily from it, and we'll see that in the actual code. Yeah, I wanted to talk a little bit about set points because there has been some history there, and I mean it's not an easy thing because there's a lot of use case. So there's a lot of ways to send set points. In the Crazyflie, we have at least 2 levels of set points you could send. The original commander, we could call it low-level commander. Now there's a high-level one. This one handles instantaneous set points. So you basically you send the set point of the state you want the Crazyflie to be at right now. And you need to send the set point at a regular interval, at least every second, because there is a 1 second watchdog. After 1 second not sending in set point, the Crazyflie will just fall from the sky. This is a safety for if you send this kind of set point of the radio and the radio disconnects, at least the Crazyflie is not going to fly away for too long. We have up to position set points in that kind, but if you want to do trajectory, typically you will need to actually plan your trajectory outside and send set points over time over this trajectory. Then we have the high-level commander that's been made by our friends from the Crazy Swarm project. And this one, the set point you send is higher level. It's things like takeoff, go to. You can upload trajectory, and for instance, sending a go to command will actually plan a smooth trajectory in the Crazyflie, and the Crazyflie will go from 0 meters per second, then go to and end up at 0 meters per second at the end. And this one actually generates a low-level set point, but from within the Crazyflie. And then we have things like the motion commander, and that is a planner, but it's a planner that works in the Crazyflie lib, that runs into Crazyflie lib. So that's kind of the idea of my schematic here. The motion commander uses low-level commander on the radio, but implements higher level commands. And those commands are, take off, but in that case, more like go forward, go backwards, left, right. It has actually been designed for the flow deck, so it is absolute height, and then it's relative X and Y position. And this is how it's going to look like. So you have your Python script that actually is exposed to these high-level commands, and the motion commander does run a loop that generates the set point and send them to the Crazyflie. And it will end up eventually in the stabilizer module, which is the control loop of the Crazyflie. So let's look at the code. This is it. So I assume you can read well. We've tested that before. So here I have opened an example that is multi-ranger push. This is in the Crazyflie lib Python under example multi-ranger push. In this example, we start by having the URI we want to connect to. There is a way to set this URI with a environment variable, but I will just modify it here because my copter here is on channel 60. Then, if we go in the code, we actually create Crazyflie, and we use a class called sync Crazyflie. That's a helper class that implements a lot of synchronous function on top of the Crazyflie. The Crazyflie object has been created very asynchronous. It was created for the Crazyflie client, which is a GUI originally. And when you control multiple Crazyflie, or while you control it from a client, it's very easy. It's easier to have callbacks and stuff. But for simple case, it's much easier to have a synchronous Crazyflie. So this is why this class has been created. This is actually going to open the connection to Crazyflie on the URI we declared above, and we will have it in this context as SCF. Then we open the motion commander. Same thing. This is one of these Python context. So we will give it the Crazyflie and get the motion commander object that will allow us to move around. And then we will open the multi-ranger the same way. So same thing, gives a Crazyflie, get a multi-ranger. So in that context, we have a Crazyflie, a motion commander, and a multi-ranger that you can use and play with. The motion commander will have made the Crazyflie takeoff. That's interesting to note. So at this point in the program, we are flying. And then all we need, that's the meat of the algorithm. And the only thing we're doing is that while we want to fly, we have this isClose function that actually basically tests if if the distance is lower than 20 centimeter, if it was. So we test multi-ranger front, back, left, right, and we actually change the velocity in X or Y accordingly. And with a motion commander, we can call the function start linear motion to actually move around. So yeah, this is basically it. And of course, a slip. This is running in a loop, and should avoid to send a set point too far, too fast. So let's try it. I have this camera. Yes, I just put the Crazyflie on the floor here. Can put the editor here so that I can see what's happening. And then the way to run this program is simply to run it with Python 3. I already have the lib installed. That is something that I've done up front. So it's got example, multi-ranger push. Apparently the spelling has to be right as well. Yes, so now we're connected, taking off, so I can push the Crazyflie around, and I actually activated the end of the flight. We have a test here that if we detect the top sensor, we will stop flying. So that's what I did with my arm. Yeah, cool. So that works. So now we've gotten our time. Is it? Oh, it's perfect. We've gotten our autonomous behavior from Python, but we want more. Now we want it in the Crazyflie. I mean, it's much nicer than you get a fully autonomous robot. and you don't need the PC anymore. So to move code in the Crazyflie, that has traditionally be a quite tricky thing. I mean, not as tricky as with other platform because this is fully open source. So at least all the code is there. You can do it. Oh, thank you, Marcus. Yes, app layer. Traditionally, it has been quite hard because you would have needed to get the Crazyflie firmware, find a place to write your code because your code has to run somehow, write it, and now you have a fork of the Crazyflie firmware, which means that over time that's going to diverge with our version. And when you give the code, or when you want to work on the code in 6 months or a year, you either need to rebase it and do a lot of Git magic, or you need to copy paste a lot of stuff, and that's pretty impractical actually. So to fix that, we've developed a couple of things. The first one is out of tree build. Out of tree build allows you to build your add code to the Crazyflie out of the Crazyflie project. So you can essentially include the Crazyflie as a library to your code. In that case, you don't actually need to fork the Crazyflie firmware, but you still need to put the code somewhere. And this cannot be in the Crazyflie firmware because we are back to the early problem. So for that, we've made an app layer, and that's basically a hook. So you can enable app equal one in the Makefile. And this will call app init during startup of the Crazyflie. And this app init has this app init has a default declaration, which will actually create a task, wait for the Crazyflie to start, and call app main. So you have the option to either implement app init if you want low-level control over what's a FreeRTOS task you want to run, or you just create app main, and this is going to be in your own task, and you can start running from there. Both these, there is one mic open at the office. Yes, both these together means that you do not need to fork the Crazyflie firmware, and you just keep the Crazyflie firmware as a Git submodule. And in 6 months, 1 year, all you need to do is bump up the version of this submodule, fix a couple of functions that have changed, and you're good to go. No need to play around with Git anymore, and that's nice. I did this page to actually show you a little bit of how does the Crazyflie start and why this having this app layer is actually a very nice thing. Because the Crazyflie firmware is based on FreeRTOS. So main.c does not do much. It actually spawn the system task and start the RTOS, and that's it, nothing else. And then the syntax task will actually initialize communication, a couple of drivers. If we jump over the app subsystem, pour run self-test, and then it will actually generate a system start set event that will be broadcasted to everything in the firmware, and that's when everything starts. It's not obvious where you should add your own code in there. So what we've done is we've just chosen one point. I think it's after the driver and before the subsystem, but this is just an illustration. And we call app init that actually creates the task. And then it waits for the system to start. And when the system started, it calls app main. So it isolates all this complexity and allows you to just run your thing without having to care too much about everything that happens on the bottom. Again, it's kind of good to know that this happens on the bottom. So let's look at some code. Yeah, I just, like for Python, I have this slide that actually explains all the code. If you want to look at it later, we will post the slides in the description of the video. But I will try to do that in real time as well. So now I am not in the lib, I am in the Crazyflie firmware. I have cloned the Crazyflie firmware. This is unmodified. And I went to example demo push, app push demo. So this is in tree because it's in our tree, but this is a completely independent project in the Git repo. It actually contains a makefile, and the makefile, and that's where the magic happen, sets the crazyflie base variable and include the crazyflie makefile. And if these two things are done, then it allows you to actually, if you make in this folder, you will make the crazyflie firmware. But before that, then we can add things. And what we're going to add is enabling the app layer, adding a vpass, which allows us to add C files in this source file. That's some make magic. Just do it. And then, so our file is called push.c. So we just proj obj add push.o, which will get make to actually compile push.c. And that's it. Now we can compile something in the crazyflie. Since we enabled the app layer, we will need to declare app main, and that is what we do here. Not sure that is needed anymore, but we apparently sleep for 3 seconds because app main is going to be called after the system has been initialized. But I guess this is some kind of safety because the crazyflie will actually be ready to fly as soon as this starts, which is what you get with making it fully autonomous as well. You get crazyflie can just jump on you. That has happened. So we need to access the log, and we've added API to get the log from within the crazyflie. So that's what we're doing here. Each log have an ID. So we get the ID of the log for all our sensor, left, right, front, back, and up. And we will we have actually added some check here to check if the decks are installed, which is very, very good. We get the param in that case to check that the deck are actually installed. You can do that. This can be good because running this code without the deck installed will be pretty bad. It's going to fly around randomly. And then again, the meat of the code is let me see. Yeah, is implemented here. So it's not ifs, but it's a branch of functions. But the end of it will be that we have the velocity in x and y, front and side, that will be calculated using the different ranges. So we get the range, calculate the velocity, and then we will set the hover set point. And send this set point to the crazyflie. This function here is actually something that we want to solve, but that's how you would do it right now. Set points in the crazyflie are defined in the pretty complex structure that can do everything and more than what's possible actually, which is a problem that we're going to solve. But so when you make an app, you need to, if you want to send a set point, you will need to fill up this set point structure with what you want to do. So right now we would like Z to be absolute, to be at some Z position. Yaw, velocity, so we want a relative yaw, and we'll like often keep it at 0, that's what's done. And X and Y velocity with Vx and Vy. And we want the velocity to be in the body of the crazyflie. So, and sending this set point will tell everything the controller needs to actually do what we want to do. So once we have that, we need to go into the example folder. I did not do it during my rehearsal, so I came back to show you that you need. It's very easy not to do it and flash something that does not actually implement anything. Again, that's because the root of the project is your app. I mean, you're using the crazyflie only as a lib here. And you need to make. And now that it's done, put the Crucify in bootloader mode. Make C load. Yes. I can, yeah. My fault, I would show you, yeah. I can actually try to connect to the Crazyfly. Yes, and this waiting for activation is actually being printed by the app. So that tells us that things have started. You can actually printf fairly easily print to the Crucify console, and that's a very good way to debug things, or at least that's one of the easiest way to debug things. And now this code is actually going to be triggered by the top sensor. And we see that this has been unlocked, and I can disconnect it, and it's still flying even though I'm not connected anymore. So this is fully autonomous. For good or bad, again, because this can jump on you if it just sits on your desk. Has happened. So now so that's about it. That's how you would run in Python and then in C. And doing this is usually a good thing. I mean, you want to test things on your PC first, and once you find an algorithm that works, then implement it in the Crazyfly. That's among the easiest way to actually implement this kind of behavior. But where do we go from there? So as I said, this app main is basically a hook that you're getting called by the Crazyfly. We've added more of those hooks, or at least the other way around, that you can set things for example, adding an out of tree estimator. So if you implement your own estimator, you can implement it out of tree in that way. More hooks should most likely be added for maybe controller or other things. So if you need anything, if you need to implement any algorithm out of tree, please tell us. We're interested to know what needs to be added. Also, we are actually experimenting with improving the build system of the Crazyfly using kbuild, which is a Linux kernel build system. One of the plans is to make it very easy to enable disable features, which means that we would be able to have niche functionality in the Crazyfly tree as well, but not enabled by default. So it could allow you to have your very special use case pushed in the firmware. And basically all we will do to it is to verify that it's still compile over time and fix it if we implement incompatibility. We cannot test everything, but this is things we're thinking about to improve a little bit the experience of implementing our custom stuff for the Crucify. The in-firmware API is a little bit ad hoc right now. It was not at all designed for being used by other people than whoever write the firmware of the Crucify. But we have started. As you've seen, we have params log and some setpoint API that you can use from outside. But ideally, we should stabilize and improve this API. So the ideal case would be to have exactly or almost exactly the same functionality in Python and in the C, so that you would be able to easily port a Python algorithm to C. And talking about that, this is a bit of a wild card, but what does anyone think about Micropython running in the Crazyfly? So this would allow people to directly port code from the PC to the firmware, because in theory, you could have similar API. I have tried. It works, but as soon as the garbage collector kicks in, everything crashes, and I could not fix it. So if anyone is interested about looking at it, might be an interesting use case for at least app. I don't believe this would be really nice for things like estimators, even though it could work in theory, might not be preferable, but for making this kind of like push demo, high level app, or even things together with AI deck, this is something that could potentially be interesting to play with. Yes, it's going to be about it. Oh, to the minute. So is there any question?
You, Arno. Okay, any questions you have, please put them in the chat. Let's see. Yeah, Micropython. Why would it be interesting?
No, as I said, yeah, okay, I thought I've communicated this. The Micropython part was my part, but it's an experiment I ran, and I think it's interesting in the context. No, I mean it would be good enough for a lot of things, like a lot of high-level behavior you might want to implement. So in that sense, it might be interesting, not going down to C. Of course, the argument against is you have to use C anyway. So why wouldn't you C? And yeah, it might add a level of complexity to the firmware, but still, it's something that exists. It's very performant, very, very performant. So it would be interesting to play with. We have enough RAM and CPU to run it, so that's a possibility. But again, I did not manage to get to work. So it's more of a call of if anyone wants to play with that, I would be very happy to see it happen.
Good call. Okay. And there's a question actually. What happens if you do a while one or a while true in the app? Can you overload the system?
Yeah. So no, that's a good news, but it's not a good thing maybe. I guess what should happen is that it should be detected. What does happen is that the app is running at the same level as the idle task, and the idle task is resetting the watchdog. So basically, nothing happens. I don't think anything else is running idle at the idle task level, priority level in the Crazy Fly. So don't quote me on that. Don't do it. Maybe we should do it to find out. But it will not crash anything. It will just silently do nothing.
All right.
Right now.
Very clear. Yeah, just the last chance for any questions. And if not, that's okay, because you need to prepare for your next workshop anyway. So I think we can already go ahead and close the recording.